we have the same mass, but with a different length. A and B. It's going to be the diatomic case too. And number 3 is the combination of these two. Okay? We have a different spacing, different mass with a different spacing. Okay? How can I draw that? Something like this. So this is A and B, and this is mass M and M, something like this. All the same, the diatomic case. And in this class, we just think about the number 1. And in homework, maybe I have given you the questions related to the number 3 or number 2. So you can apply the same story to get the solution in each case. And in this case, what we are going to do is we have to make a reference of 2 atoms, light atoms and heavy atoms. So the light atoms, the large, let's say large atom displacement, we call this psi r, okay? And small atom displacement is going to be called zr, okay? And then we're going to have 2 equations for this case. One is, let's say, Mn. One is rth atom of large atom, and the other one is rth atom on the light atoms, something like that. Okay, and this is the r minus 1, A, and this is Ra. Okay, one is the reference to this force up and down, and the other one is going to be related to the force up and down in between these two. So there is one equation corresponding to this relation, and then the other equation is going to be related to this equation, the situation, all right? So the equation number 1, we solve that just like the monatomic case, only the difference is we have a different etas. One eta is related to the F over MA, and then the other one, F prime, is the F to MA. Only the difference is this. The other things are exactly the same, what you have done for the monatomic case. And then this equation 1 is going to be related to the Newtonian, MA, and then this A is related to the round T square over round square psi, right? And then this one is going to be related to the MA, of course. MA, large MA, and then that is going to be the round T square over round square Z, something like this. So you really don't have to go through all the mathematics. You just ask your younger brothers who is in high school. I think it has to be in high school. The middle school maybe. So you end up with the equation number 1. Number 1 is going to be round T square over round square psi r is equal to eta m zr minus 2 eta m psi r plus eta m ZR plus 1. And the equation number 2 is going to be round T square over round square ZR eta M psi R to eta M ZR plus eta M psi R minus 1. Something like this. All right? And then you do the mathematics, simple mathematics. You can quickly get the answers looking like this. A over B is going to be 2 eta M cosine Ka or omega square over 2 eta M. And this is the amplitude of two equations. In other words, the psi R is going to be A e to the minus I kx. X is going to be R times A. R times A, something like this, minus omega t, right? That is a general solution for the psi R, okay? For the ZR, we are going to have some equation solutions like this. And then here, the A and B just show us the amplitude of the wave. So by solving this equation, what we are going to have is that the ratio of two waves, one wave is correspond to the atoms with large size, and the other wave B is the amplitude of the wave of small size, okay? And then the wave amplitude ratio will have this correlations of that. And dispersion relations, you end up with omega square is equal to psi m plus psi small m plus minus root psi m plus psi small m square minus 4m small m sine square Ka. That looks complicated, but it is not complicated when you have extreme cases. When K is equal to 0, you're going to have two solutions. Okay? You're going to have a plus solution and a minus solutions. And the plus 0 case, you end up with 2 eta m plus small eta m. Okay? And then the amplitude ratio coming from here is going to be minus 8m over 8 small m. All right? And another solution, because it's a second order equation, you're going to have 2 eta m small m over eta m plus eta small m k square a square. And then you can see that, amazingly, that is a non-dispersive system. All right? And A over B, here in this case, A over B is just 1. What does that mean? The movement of the large atoms and small atoms and the same amplitude. That is an acoustic wave, isn't it? So just looking at that, we can see that in dispersion relations, omega versus k, when k is equal to 0, nearby the 0, we have one is the acoustic wave straight line, non-dispersive system, and then the other one is somewhere around here, where the value is, omega value is what? Square root of 2 8m plus small 8m, something like that. That is the omega values. We have two values when omega is close to 0. And then we have to think about the other one where the k is equal to pi over a. 2 pi over 2a, maybe. Pi over 2a. Okay? Then what happens in the k equal to pi over 2a? When pi is equal to k equal to pi over 2a, omega square is going to be 8m plus 8 small m plus minus 2. 8m plus 8 small m square minus 4 8m 8 small m sine square ka. Okay? And this sine Ka is going to be when the K value is equal to, at K is equal to pi over 2a. This is equal to 1, right? So this one ends up with small m, large m, plus minus small m minus large m. Okay? So that plus pi over a, then this is going to be small m, and a over b is going to be minus 2 eta m cosine Ka over omega square minus 2 eta m, so that it's going to be 0. What does this mean? One value is going to be something like this. What happens to the other one, the other solution of this? Let me go through the other ones. That is going to be 8 large m, and then a over b is going to be infinity. So one value is here, large m is going to be, let's say, something like this. So square root of m, okay? And then let's say here, that is the square root of m. Since eta is f over ma, small mass, it's going to be a large number. So this is going to be related to something like this, and then this is just go something like this. The important thing is, at this range, okay, omega minus range, minus 0, the atomic is going to move in the same directions. So that the center of mass is going to be moved. But here we have A over B, where is it? It's something like this. So at this case, the large atom moves long distance. The small atom moves the long distance, and large atom moves the small distance. The center of mass is not going to be changed. Okay? Something like this. That is this. The movement is minus sign means it moves the opposite directions, and the ratio is going to be the inversely proportional to the mass itself. So the atomic movement, the wave is going to look like this. Something like this. Here the wave is going to look like this, okay? So this is going to be called optical mode. This is the acoustic mode. All right? Now, what happens in this case, it means that at this part, one of the atoms is not moving, and the only big atoms is moving in this case, so that the wave is going to look like this. And in this case, the heavy atoms are sitting in the rest position, and small atoms is going to move. Because the amplitude is the infinity. And the amplitude is 0 in one case. Okay? So that is the situation that we are going to have, and we call this the pi mode. The name itself is not important. We just call it the pi mode. Just name it like a pi mode. Okay? And the next Monday, we are going to talk about the, let me see. Let me just finish this class by introducing the rest-Strahlen absorption. Rest-Strahlen absorption. Absorption means the lattice, the solid can observe the light, okay? And if you draw the omega versus k for the light, you may draw the lines very close to here. Almost the same to the y-axis here. Because in the light, the k value is extremely small. Smaller than the lattice k. So if you want to draw the light in the same omega versus k scale of the lattice wave, you have to draw it very close to this y-axis. But there is some point here which is matching. The lattice wave, optical mode, the lattice wave, and the light wave omega versus k, there has to be here, somewhere. And then that is what's going to happen is that the resonance. What does resonance means? The light frequencies and the lattice atom frequencies are exactly the same. So that the light wave shows the resonance effect, which means the light is going to be observed suddenly at this particular wavelength of the light. And that is specific. That happens only in a specific wave number, k. And that is a unique feature that is different from material to materials. And that happens in the ionic materials, because in the ionic materials, F can be defined clearly. In the covalent bonding or the metallic bonding thing, the F cannot be defined clearly like ionic materials. So especially in ionic materials, when you shine the light, then you measure the observance of the solid, you suddenly have one absorption, very big absorption at the specific light wave number. Then you can see that the reciprocal absorption happens. And if you know experimentally the K values where the absorption happens, then you can calculate the atomic binding force, F, of the solid. Because that is related to this. Okay? That is the omega is related to this, specific. And then the phi m and the phi m, all those things are F over ma. So if you know the value, omega, then you can find the F. So retrostraling observation is very important in finding the bonding energies of the ionic materials. And there is an example for the retrostraling observations. And then finally, when you have n atoms in multi-atoms case, you are going to have 3 longitudinal wave, 2 longitudinal wave, and one longitudinal wave and 2 transverse wave. And then you are going to have a m-1 multiple optical mode. Oh, right, yeah. When you have n atoms in your system, then you're going to have 2 transverse wave plus 1 longitudinal wave for the acoustic mode, and then the rest n-1